So when we introduced inverses, we saw that a matrix A, B, C, D has an inverse if and only if AD minus BC is not equal to 0. And we've also talked about inverses of bigger matrices, like n by n matrices, and it would be nice to have a condition like this to determine whether a matrix is invertible. And it turns out there is a condition. So an n by n matrix has an inverse if and only if its determinant is non-zero. So we're going to define determinants today. Okay, so given an n by n matrix A, we're going to produce a number called det A, just a number, and this number is non-zero if and only if A is invertible. So here is how I like to define the determinant. So it's something you have to do to your matrix, right? So you pick an entry from each row, and you do it in such a way that no two of your choices are in the same column. And there are two ways of doing this if you're a 2 by 2 matrix. If you pick A from the first row, you have to pick D from the second row, because C is in the same column as A. If you pick B from the first row, then you have to pick C from the second row, otherwise you're in the same column. So there are a number of different choices you could make here, and we're going to make all possible choices, but sort of one at a time. So pick one entry from each row in such a way that no two are in the same column, and multiply all your chosen entries together. Now do the same for every other choice that you could have made. So do this for every choice that you could have made. So at this point we would have AD and BC if we were 2 by 2, and finally you add up all the answers with signs. So I'll tell you how to decide whether to put a plus or a minus sign in front of each thing. So this is going to be plus AD and this is going to be minus BC, and you add them up and you get AD minus BC. Okay, so I will explain how you get these signs in a moment. First, let's just look at how many choices there would be for a 3 by 3 matrix, and I'm going to write it as A11, A12, A13, A21, A22, A23, A31, A32, A33. So how many choices are there? Well, if you pick A11 from the first row, then you can't pick anything in the first column or anything in the first column for your other choices, so you have to pick something like A22 in the second row, and then you'd have to pick A33 in the third row. Or you could do A23 in the second row and A32 in the third row, along with your A11. That's another valid choice. And now moving along, if you pick A12 in the first row, then there's two choices. Below that you could do A21, A33 here and here, or you could do A12, A23, A31. That's here and here. And finally, if you picked A13 in the first row, then basically you have these two choices in the second and third rows, so A21, A32 and A13, A22, A31. Okay, so there's 6 possibilities. And if you thought about the same thing for 4x4 matrices, you'd end up with 24 choices. And very quickly you start realizing that the number of possible choices for an n by n matrix is n factorial. And you can see that because well, there's a relationship with permutation groups. So for each choice, write down the column numbers in order, in the order you picked in the rows. So you know, this blue choice would be 1, 2, 3, because I'm picking from columns 1, 2 and 3, but the red choice would be column 1, column 3, column 2. For this first green choice I'm doing column 2 first, then column 1, then column 3. The next I'm doing column 2, column 3, column 1. And over here I'm doing column 3 first for the orange guy, and then columns 1 and 2, and then finally 3, 2, 1. So for each choice you write down the column numbers in order. This gives a permutation of 1, 2, 3, or more generally 1 up to n. So the number of choices is the same as the number of permutations, which is n factorial. So this is to prove this fact. Now I can tell you how to pick the signs. So the sign of your choice, as in of the choice you made, is +1 if your permutation is a so-called even permutation, which means that it's obtained by doing an even number of flips, where you just flip two things. Or transpositions. And it's -1 otherwise, if you do an odd number of transpositions. Let's do an example. 1, 2, 3. To get back to 1, 2, 3, I don't have to do anything. That's an even number of flips. It's 0 flips. So here the sign will be plus. 1, 3, 2. Well, I've flipped 2 and 3. So that's 1 flip, so the sign will be minus. Here, 2, 1, 3. Well, if I flip 1 and 2, I get back to 1, 2, 3. So the sign is minus, that's 1 flip. Here, 2, 3, 1. How would I get back to 1, 2, 3? Well, I've flipped the 1 and the 3, and then I flip the 1 and the 2. Let's just do the intermediate steps. If I flip these two, I'd get 2, 1, 3, and then if I flip these two, I get 1, 2, 3. So this is 2 flips, so this would be a plus. This guy is a plus, and this guy is a minus. You can tell this because it's a cyclic permutation of 1, 2, 3. Okay, so the determinant of a 3 by 3 matrix is therefore let me get all the terms together. It's A11, A22, A33 with a plus sign, and then minus the next term, so minus A11, A23, A32, and then what was this? This was also a minus sign. Minus A12, A21, A33. This was a plus, plus A12, A23, A31. And then plus A13, A21, A32, and then minus A13, A22, A3. Just going back to 2 by 2 matrices, A and D, that corresponds to the permutation, which is the identity, just 1, 2. And BC, that's 2, 1, which to get back to 1, 2, you'd have to do a flip, and that's why there's a minus sign there. Okay, looking at, I'll get a new page. Looking at this colourful formula at the bottom here for the 3 by 3 determinant, we can see there's going to be a nice way of writing this in index notation, a more compact way. So let me just tell you what the formula is. The determinant of A, and this is going to work for n by n matrix, is the sum over permutations. So sigma is going to be a permutation of n objects, so the notation is sigma lives in the group of permutations on n things, the symmetric group. And then there's a sign called sine of sigma. That is either plus 1 or minus 1 if the permutation is even or odd. And then there's a product of things A up to A. The first guy is coming from the first row, so this index will be 1. The second guy is coming from the second row, so this index will be 2. The last guy is coming from the last row, so the first index will be n. And what to put here? Well, in this case, remember this corresponded to the permutation 1, 2, 3, and you can see that you're putting 1, 2, 3 as the second index at the bottom. Here, this corresponded to 1, 3, 2, and you're putting 1, 3, 2 as the second index, and so on. So actually what you put here, I need a bit more room, is going to be sigma of 1. In other words, you apply the permutation to 1. Here it's sigma of 2. Here it's sigma of n. Okay, so this is the index formula, or index notation formula for the determinant. It's just rephrasing what I said above as a formula. Let's do some examples because it's otherwise a bit mind-bending. So let's take this matrix. What's its determinant? Well, there's only one way of picking something from each row in such a way that you don't pick any zeros, right? Because if you pick a 0, then when you multiply everything together, you're going to get 0. So you have to pick you have to pick this one, and this one, which is going to give us 1 times 1 times 1, which is 1. So this sum is just one term. And what's the sign? Right, this is the permutation 3, 2, 1. In other words, 1, 2, 3 goes to 3, 2, 1. Because we're picking from the third, then the second, and the first column. To get back to 1, 2, 3, we'd have to do how many flips? We'd have to flip 1 and 2. We'd have to flip 3 and 1. And then we'd have to flip 2 and 3. That's 3 flips. Oh, we could have just flipped 1 and 3. Yeah. But it's still an odd number. So it's a minus sign. So the determinant of A is -1. And actually you've just seen in this example why this sign is a sensible thing to write down. So I said permutation is either the product of an even number of things or an odd number of transpositions. Here you can express this permutation as one transposition where you just switch 1 and 3, or you can do it as 3 where you switch 1 and 2 and then 1 and 3 and then 2 and 3, but that's still an odd number. So this is a theorem which I'm not going to prove, which is that any permutation can be written as either an odd number of transpositions or an even number but not both. In other words, the signs that we're assigning to these terms are well defined. Let's do another example. Let's take a diagonal matrix. I don't know, like 5, 1, 3. This is fantastic because there's only one choice, one valid choice that we can make with no zeros, which is 5, 1 and 3. So the only contribution we get is 5 times 1 times 3, and that comes with a plus sign because it corresponds to the permutation 1, 2, 3, because we're picking something in column 1, column 2 and then column 3, and that you don't have to do any flips to get back to 1, 2, 3. So the determinant is 15. So if you have a diagonal matrix with only entries on the diagonal, then the determinant is just the product of those entries. With no extra sign. More generally, let's say I had an upper triangular matrix, something like 1, 2, 3, 1, 2, 1. So all the entries are on the diagonal or above it. Well, there's only one way of picking anything from the last row. You have to pick this guy. So you can't pick from the last column anymore. So there's only one way to pick anything from the second row, that's here. And there's only one way to pick anything from the first row then, which is this one. So there's only one term in the determinant, which is 1 times 1 times 1. so the determinant is 1. And again, the sign is plus because it corresponds to the permutation 1, 2, 3. And again, this is true for any upper triangular matrix, in other words, where the entries are on or above the diagonal. The determinant is just the product of the diagonal entries. Some important corollaries of this, which we're going to use heavily later, are that if we take the elementary matrices Eij lambda and Ei lambda, they are going to have determinant 1 and lambda respectively. Why is that? Well, remember, Eij lambda has 1s on the diagonal and it has a lambda somewhere off the diagonal, either above or below, and everything else is 0s. And the same argument, so if it's above the diagonal, we've just said upper triangular determinant is the product of the diagonal entries, so the determinant is 1. Exactly the same argument applies for lower triangular things. So that works for all elementary matrices Eij lambda, and Ei lambda, remember, was 1s on the diagonal everywhere except one position II, which was then lambda. I'm not sure why my lambda is so wobbly. And that's a diagonal matrix. Everything else is 0, so the determinant is just 1 times 1 times 1 times lambda times 1 times 1 times 1. In the next video, we're going to prove some properties that the determinant has, and how it behaves under certain row operations, which will give us a way of computing the determinant. As in, easier than just substituting into the big messy formula that we had earlier on.